Now, the one thing that we were doing was the last thing is finding relative atomic mass. And called, there's a thing called mass spectroscopy that helps us in finding. Mikhail, all of them would be solved using that. Okay? The other methods are very lengthy. So, relative atomic mass. Questions on relative atomic mass. That's the last thing we're going to do. And iske andar there's you just need to have a very brief. A2 ke andar you'll study this in a lot of detail. Actually, in it's a whole chapter. But over here, you need to have some idea of what mass spectroscopy is. Okay? And just a very brief idea of what mass spectroscopy is. It helps in finding the mass of an atom. How do they figure out the mass of an atom? That they have a ionization chamber. In that ionization chamber, they bombard it with electrons. So there must be a molecule or an ion. For example, there's a Cl2 molecule that's in it, and it's going to get bombarded by electrons. Now, the purpose of this bombardment is that you need to ionize it, and as a result, this Cl2 would either turn into an ion, or the molecule would break down and it would form fragments, tiny fragments that are basically atoms. So the molecule might break down. As a reason, I've written plus one is that any sort of ion is possible. Like if you have a Cl2 molecule and let's say you have two Cl atoms and they're both combined together. Okay, so you have two Cl atoms. Now any type of ion is possible when this Cl2 molecule gets bombarded by electrons. But the thing is that the whole mass spectrum is kind of calibrated to only detect plus one ions, because all other ions they get deflected so much that they're not they basically they're not detected by the detector. Tika, I'll explain that to you. Just the beginning part. A chlorine molecule gets ionized, ends up forming plus one ions. This is known as a molecular ion because the molecule is intact but it has been ionized. So from somewhere, one electron, because of the bombardment, for example, this electron is lost. So anything could happen. Or the other thing that could happen is that the bond between the Cl2 molecule would break and you'll get a Cl atom that's going to get ionized as well. That's called a fragment. So it's basically a smaller piece of the original molecule. So this is known as a fragment. Now the next part that they do is that they turn it by using electrodes, negative electrodes in most cases. So by using negative electrodes, these positive ions are turned into a beam. So Cl2 plus 1 and Cl plus 1, they all get attracted to one side and they form a beam. You can just 1 second, let me take a question. I said, Usman, just quickly. Mass spectroscopy, you just need to, this is a whole chapter in A2 and you just need to have a brief overview. What then happens is, remember, we are trying to figure out the mass of the particles. So what happens then is that there's this magnetic field over here. And if you know some physics, then charged particles they get deflected by the magnetic field. So all these particles that are coming in, this beam over here, it's going to get deflected. All these particles they're going to get deflected in different directions by that magnetic field. Now the okay, so hopefully everyone knows that magnetic fields they deflect moving charged particles. You studied the left hand and the right hand rules. One of the rules probably applies to this. Probably the motor rule, I think, the left hand rule. As anyways, you have a magnetic field, particles are getting deflected. Now, what does that deflection depend on? The deflection is directly proportional to the charge of the particles. So if the particle has a higher charge, like +2 or +3, then it's going to get deflected so much that it's going to go out. I mean, we have a detector over here that's detecting or collecting all those particles and detecting how much, what amount of each particle is that you're getting over here. So if the charge is too high, like you could get +2 over here, you could get +3 as well. I mean, it's not always one electron getting knocked out; it could be more than one. So the problem with +2 and +3 would be that the deflection would be so much that the detector would fail to actually detect them, which is why your detector is calibrated in a way that it's only at those positions where you're going to get +1 particles, which is why mass spectroscopy only actually detects +1. So you're never actually dealing with +2 or +3 particles, or even -1. Cl could form a -1. It might gain an electron, and it's very likely to gain an electron. So if it gets a negative charge, then the deflection would be in the opposite direction. And again, you don't have a detector over there, so your detector would not actually detect those particles even. So at the end of the day, you're actually just focusing on the +1 particles. So deflection is proportional to charge, and at the same time, deflection is inversely proportional to the mass. Now, the charge of the particles is constant in your case. You have set the detector in a way that you're always detecting +1 particles. So the deflection in your case, you're keeping the charge constant. So it's basically just inversely proportional to mass. And by measuring the deflection, you can actually get some idea of the mass of the particle, because mass is inversely proportional to deflection. Heavier particles, they're not going to deflect very much. Light particles will get deflected a lot. Now, I'm going to talk about the particles now just a bit. First thing, Cl2 plus is your heavy particle. It's not going to be deflected that much. But how many different types of Cl2 plus one do you have? The thing with chlorine is, hopefully everyone knows this, that there are two types of chlorine. There's 35 and there is chlorine 37, right? So there are two different types of chlorines. So if you talk about the Cl2 molecule or Cl2 ion, uh, the Cl2 ion is going to have three different masses. There are three different possibilities. For example, Cl2 plus 1 could have a mass of 70. Why would it have a mass of 70? Because if both Cl atoms in it are have this isotope. Okay, Cl has two isotopes. One is 35 and the other one is 37. Similarly, you could have a Cl2 plus 1 which is 72. Why would it have a mass of 72? Because if one of them is 35 and the other one is 37. Or you could have a Cl2 plus ion with a mass of 74. That's because both of them might be 37. So there are three different combinations. The Cl2 ion can have three different masses. So I'm just going to draw, these are the heaviest particles. So they're going to get deflected the least. So the 74 one, Cl2 plus 1 having a mass of 74 is going to be deflected the least because it is the heaviest. So you're going to get it somewhere over here. Then you're going to get Cl2 plus 1 again, but this time the mass is 72. The reason it's deflecting more is because the mass is slightly lesser. Then you're going to have Cl2 plus with a mass of 70, and that's going to be deflected even more. Why? Because it's lighter. So you're going to get all these deflections, and your detector would deflect all of them at different positions, at different angles. And based on the deflection, you can figure out the mass. There must be a constant over here. You put in the deflection, you get the mass of the particle. I say, anyways, then there would be these fragments coming in. Lots of fragments, tiny fragments. The fragment is basically Cl plus 1, so you're going to be getting fragments of Cl plus 1. Now, Cl plus 1 is easy because there are only two types of Cl plus 1s. One is 35 and the other one is 37. So there is no combination. It's either going to have an atomic mass of 35 or it has an atomic mass of 37. So I'm going to just remove this one. So you're going to get a deflection of Cl plus 1, 35. This should be 37 because 37 is heavier. And you're going to get a deflection of Cl plus 1, which is 35, right? So these are your molecular ion, and the ones over here are your fragments. So we're going to focus on the fragments. Based on the deflection, you get the mass of these particles. Now, no one is really going to ask you in detail about the working of the particles. You should know this thing. The deflection is proportional to charge and inversely proportional to mass. This is very obvious because if the charge is higher, it's going to get deflected more. If the mass is greater, the deflection would actually be lesser. So you must know this, okay? Because there has been one question where they had asked to figure out the position or of where you're going to get or the angle. They asked you to calculate the angle. Okay? I'm going to do that question in a bit, but let's come back to this and focus on the fragments. Just give me 1 second. Now moving to the type of questions. I'd say your detector over here is basically detecting charged particles. So the detector is getting this current. I mean, the detector would be getting a current at this point, and it's going to be getting a current at this point as well. I mean, charged particles are basically there's a flow of charges. Flow of charges is current. So there's going to be an emitter over here that would be detecting a reading over here. Now the amount of current that you get, that's basically that gives you kind of gives you the percentage abundance. So there's a thing called percentage abundance, which is, I mean, this axis is usually the mass to charge ratio. The charge is 1. E represents charge. So the charge is kept constant at 1. So basically, this axis represents mass. Now you're getting a detection at 35 and you're getting a detection at 37. So right now, we're not really focusing on the molecular ion. I'm just focusing on these two. So there are two types of chlorine. The two types of chlorine, one has a mass of 35, the other one has a mass of 37. And there's going to be a current detected at these 2 points. I mean, if there are more particles coming in, like for example over here, there are more particles coming in, then there's going to be a higher current obtained over here. If there are fewer particles coming over here, then there's going to be a lower current over here. So the relative amounts of currents that you're getting, they give you the abundance of these particles. So this axis over here usually represents percentage abundance. And in the case of chlorine, it's 75%. They might give it in terms of percentage, 75% or 25%, or they might give you ratios. So 3:1. Now, in both cases, make sure that you convert the percentage in whatever ratios are given. You convert that into percentages uh, or fractional percentages. That would also work. So for every three particles detected over here, uh, one 3:1 means there's going to be for every three particles that are detected at 37, not at 35, you get one particle detected at this point at this position. So if this over here you're getting a current of 1 ampere, over here you're going to be getting a current of 3 amperes. Okay, so that's the relative percentage abundance of these two particles. And you're going to be asked to find the relative atomic mass. So there's a simple formula for finding relative atomic mass. Now, relative atomic mass, remember, should be in decimals. I told you right in the beginning, it's never a rounded value. Plus, it's the average mass of isotopes based on the relative abundance. And the formula for finding relative atomic mass is there's a simple formula that you have to memorize, and that is uh, you're going to sum up the percentages multiplied divided by 100, or this is known as the fractional percentage, and you multiply it by the isotopic mass. And you're going to sum or collect all of the terms and that's going to give you the average. What this formula basically means is it's a way of finding averages, because so how do you find averages usually? I mean, this formula over here, it's simply a formula for calculating the average. Like for example, for if there's 75% chlorine 35s and there are 25% chlorine 37. So if you use this formula, you're going to get an average. So just a little logic about how this formula works. What happens is the old method that you know of calculating averages, that if there are four numbers given, like there are twos given and there are threes given. Like these are four numbers. There's two, there's another two, there's three, and there's another three. Now the old method of calculating averages, you sum them up and you divide them by four, or the number of terms, and you get the average, which in this case would be 2.5. But this formula would fail if the numbers are too many. Like if there are 1,000 twos, you can't just do 2 plus 2 all the time and and go for 1,000 terms. So if there are lots of numbers, then you have to invent a clever way of doing the same thing, which is add them up and then divide by the total number of terms. Now that way is that you know that 50% of the time you're getting twos, and the other 50% of the time you're getting threes. Uh, or what we can do is we can add another number. Okay, let's say there's a 5 as well, and I want to figure out the average. So based on percentages, this is 40%, I think. Like two times out of 5, you're getting twos. 40% of the time you're getting threes, and 10 or 20% of the time you're getting fives. So the new way of finding averages is that you take 40%, divide by 100, and you multiply it by whatever the number is, which is 2 in this case. The next one, again, it's 40 divided by 100, and you multiply it by the number which is 3 in this case. And the last one is 20 over 100, and you multiply it by 5. So you're going to get exactly the same answer, percentage multiplied by the value, and you sum them up. Percentage multiplied by the value, percentage multiplied by the value, percentage multiplied by the value. And you sum them up, it's going to give you the same answer as doing 2 plus 2 plus 3 plus 3 plus 5 and divide the whole thing by 5. You can do this in this case, but if the numbers are too many, okay, for example, there are million numbers, and you know that out of those million random numbers, 40% of the time you're getting twos, 40% of the time you're getting threes, and 20% of the time you're getting fives. So this is the formula that you're going to use. तो इसके अंदर भी आप यही करोगे. So how would you find the relative atomic mass? The percentage is 75% of the time you're getting 35. So it's going to be 75 over 100 into 35, and 25% of the time you're getting 37. Okay, you do this and you calculate this and you get 35.5. So that's how you're going to take the average of the isotopic masses. Uh, is this formula clear to everyone? Yes or no? We're just going to do a couple of questions. They're over here. Now, the questions would be, uh, for example, look at this question. This is one example question, and you're given isotopic masses. So so let's sorry. So let's try and solve this. I said, remember, I told you that masses are never whole numbers. In the initial lecture, I told you that one thing that I told you clearly was that this is the nuclear number. If they're stating this as a whole number, then this is the nuclear number. The nuclear number and the isotopic mass are pretty much the same, except that nuclear number is always a whole number because it's the sum of the neutrons and the protons. So you can't have 1.1 protons. But the mass is always in decimals. Okay, whenever you talk about mass, because Whenever we say a proton has a relative mass of one, it isn't actually one. Okay, it's close to one, but it's not exactly one. So whenever you have these masses, it's always going to be in decimals. As anyways, the question over here. In this question, the final AR has already been calculated. It has four isotopes. So there are four different isotopes, and what you need to do is you need to calculate this. I think both these values. I mean, the whole question is about this. I think use these data to calculate the relative isotopic mass of the fourth isotope, which is this one. So one thing about percentages is, so you have four isotopes. So the total percentage is always 100%. Sometimes the total percentages should be 100% of all the isotopes. Now they've given that 0.185% is this one, 0.251% is this one, 88.45% times you're getting this one. So what is the percentage over here? So you're just going to subtract it from 100. So let me take out my calculator. So it's going to be 100 minus all the percentage, 0.185. The other one is 0.251, 251, and the last one is 88.450. And the answer I get is 11.114%. So over here, the value is 11 point. Let me, so it's 11.14%. That's the value I'm getting. Now, based on that, the formula that we did was that the AR is basically, now we have the AR, the value is already given. So the AR is basically uh, the mass of the isotope into the percentage. So it's going to be 0.185. And remember to make sure you divide by 100 because it's fractional percentage into 135.907. The next one is percentage multiplied by, I'm going to sum up all of them. So it's going to be percentage 0.251 divided by 100 and multiplied by 137.906. Then I have 88.450 divided by 139.905 into, this is wrong, divided by 100 and then multiplied by the value. And you're going to multiply it by 139.905. And the last one is 11.14%. So it's 11.14 divided by 100. And I'm going to multiply it by the value, which I don't know. So this over here is your X. And the AR is already given. That's given as 140.116. You can do the calculation. Remember, there's a lot of chance of making a lot of mistakes, especially when your calculations have a lot of addition and subtraction. So plenty of mistakes, silly mistakes are possible during your calculation. So you can try and calculate and always follow the instructions. It should be accurate up to three significant figure. You can find the value of X in this way. Okay. Is this question, you can solve this at your end. Okay. Is this question clear? Yes or no? Is this clear? And most of the questions, Usman, is this clear? Mikhail, is this clear? Sanjida, is this clear? So most of the questions would be like this. Okay, for example, if you look over here, it's the same graph, percentage abundance is given, and you're being asked to find the relative atomic mass of what substance. This is element X. So these are all the isotopes that you have. So multiply the percentage by the number, add them up, start adding them up, and it should be fractional percentage, so it should be 74 divided by 100. Or what you can also do is you can add them all up, you can multiply them, all of them, and then divide by 100 the entire thing. So there was one question that was slightly tricky. All of them are pretty much the same, and you have to do exactly the same thing, just apply the formula, that's it. So you can try these questions, most of them are exactly the same. Now I wanted to move on further. I'll give this as an assignment later. ठीक है, most of the questions just apply the formula. Now